Remember these? In 2008, I tried the classic photochemical two-faced demonstration with thionine dye using an old-school overhead projector, but I was left unimpressed by the effect. The lamp was blinding, refraction from the round beaker distorted the view, and the moment that you turned the light off, the color rushed back before your eyes could adjust. But in 2024, I saw a post from Angus Alchemist, which led me to a more satisfying effect with a chemical you probably already have in the prep room, methylene blue. Some of you might have thought about doing the thionine demonstration, but were put off that you didn't have any in stock. But methylene blue has a very similar structure, and the addition of methyl groups to the amines makes it a little slower to react, which actually makes the methylene blue variation of this experiment more forgiving. Setup is straightforward. We start by dissolving 0.4 grams of iron 2 sulfate, heptahydrate, and 0.4 grams of citric acid into about 100 milliliters of deionized water. And to this, we add around half a ml of a 0.1% methylene blue solution. You're looking for a final hue that mimics a standard 0.5 molar copper sulfate solution. Transfer about 50 milliliters of that into a cell culture flask and cap it tightly. Let the solution settle and then place it over one of these LED work lamps in front of a white wall, or even better, a light panel for animators. Use an opaque card to mask half of the light and you'll see the illuminated section bleaches. The color slowly returns when the light is removed, slower than it does for the thionine variation, and this makes it easier to see if you get dazzled when the light is on. There's an interplay of thermodynamic, will it happen, and kinetic, how fast will it happen, effects taking place. To bleach the dye, we need to reduce it, as this disrupts the extended conjugated system extended over both rings of the dye. The reduction potential for iron 3 to iron 2 sits at plus 0.77 volts, and that's available in most data booklets, while the reduction potential for methylene blue plus at pH of about 2.5 sits at around plus 0.3 volts. If we calculate our cell potential, delta E equals the E reduction minus E oxidation, we get plus 0.3 volts minus plus 0.77 volts equals minus 0.47 volts. We find a negative cell potential, telling us that this bleaching reaction is non-spontaneous in the dark. The dye shouldn't lose its color. To force the reaction to happen, we have to do work on the system, and that's where our LED light comes in. Methylene blue's absorption peak is at the red end of the spectrum at 664 nanometers. When a photon of red light hits the methylene blue plus ground state, it launches it into a short-lived, highly energetic excited state. And in this excited state, its reduction potential skyrockets to plus 0.43 volts. It becomes an even better oxidant than chlorine. Now, delta E becomes highly positive. The thermodynamics flip and the iron 2 successfully reduces the excited methylene blue dye into its colorless, protonated leucoform LMBH3 2+. We can show the importance of light at wavelengths that the dye can absorb with the use of some filters. While purple or blue filters won't affect any kind of bleaching, a red or a yellow filter placed in front of it will actually bleach the dye. This is no purely thermodynamic effect though, and if you swap the citric acid for acetic acid and run at the same pH, the effect fails. It turns out that an alpha hydroxy acid, malic, lactic, tartaric, etc., is essential. And Angus Alchemist's original post plays with a number of these by making up the reaction mixture in various juices and sodas. Why is that alpha hydroxy group essential? Well, it's almost like a Swiss Army knife of problem-solving tools for this reaction. By chelating iron 3, it significantly reduces its concentration in solution, and then it keeps the backwards reaction slow. This also keeps the iron reduction potential low, making the bleaching process still more favorable in the light. The acid also massively boosts the bleaching reaction kinetically too. And if you think about it, two positively charged ions coming into contact in solution close enough to exchange electrons, they're going to need as much help as possible. The excited state of the methylene blue is very short-lived in solution, so we need to use it as soon as it appears. A small number of the citrate ligands will be charged at this pH, and that helps a little by reducing the overall positive charge on the ions, and this allows for more frequent close collisions, but the real kinetic trick is the alpha hydroxy's ability to help shuttle electrons and protons quickly. I couldn't believe that you could see so much going on with some household chemicals. The story doesn't stop there though. The colorless leucoform of the methylene blue doesn't just not absorb anything, the absorption peak simply sits in a different part of the spectrum that we can't see. In our next video, we'll leverage that absorption band to show how the bleaching process can be flipped on its head and make color reappear from a bleached dye using a different kind of light source. So look out for that one when it drops.